Your AI is lying to you. Worse. It sounds perfectly convincing while doing it. We call it a hallucination, and it's one of the most critical vulnerabilities in modern artificial intelligence. Large language models are undeniably powerful, but their architecture relies on predicting the next most likely token in a sequence. Because they lack true cognitive grounding, they are prone to confidently fabricating facts and breaking logic. It's the AI equivalent of a silent system crash disguised as a successful operation. So, how do we fix this? Today, we are debugging this flaw and exploring two advanced agentic reasoning frameworks engineered to patch these vulnerabilities: Tree of Thoughts and Chain of Verification. To understand the solution, we must first understand the bug. Standard interactions with LLMs, and even advanced techniques like chain of thought prompting, operate on a linear execution path. The model moves straight from the problem statement to the solution. But what happens if the model takes a wrong turn at step 2 of a 10-step logic puzzle? Because it generates tokens sequentially, it gets trapped. It cannot easily undo its mistake. Instead, it tends to double down on the error, weaving a complex web of logical inconsistencies just to justify that initial wrong turn. If the foundation is flawed, the entire final output is compromised. We need a way for the AI to hit Ctrl-Z, evaluate its path, and try a different route. Enter Tree of Thoughts, often abbreviated as TOT. This framework completely reframes the generative process. Instead of treating text generation as a linear pipe, Tree of Thoughts treats it as a search problem over a complex tree of potential decisions. It allows the language model to explore multiple reasoning paths simultaneously. It evaluates the promise of each path as it goes, and crucially, it can backtrack if it detects that a path is leading to a dead end. Think of it less like a calculator printing out a formula, and more like a chess master evaluating dozens of potential future moves, discarding the weak ones, and pursuing the strongest lines of play. The Tree of Thoughts framework is built on 4 core components. The first is thought decomposition. You cannot solve a massive architectural problem in a single bound. The complex problem must be broken down into intermediate, manageable steps. These intermediate steps are the thoughts. Depending on the problem, a thought could be a single line of code, an equation, a paragraph of a story, or a specific logical deduction. By breaking the problem down, we give the model granular control over its own reasoning process, allowing it to evaluate its progress at every single milestone. Once the problem is decomposed, we arrive at the second component, thought generation. At each step in the process, instead of generating one single immediate answer, the LLM is instructed to generate multiple distinct possibilities, or reasoning branches. We call this parameter k. For example, if k equals 3, the model will brainstorm 3 completely different approaches to solving the current step. This injects necessary diversity into the reasoning process. It forces the model to think outside the immediate, most obvious, and potentially flawed next token, and instead consider a spectrum of strategic options. Generating multiple thoughts is only useful if we know which one is best. This brings us to the third component, state evaluation. In this phase, the language model acts as its own internal compiler and testing suite. It uses a heuristic prompt to score each generated thought based on its likelihood of solving the overall problem. The model might categorize the state of a path as sure, maybe, or impossible. If a thought is deemed impossible, the system instantly prunes that branch, saving compute resources and preventing the model from spiraling down a hallucinatory rabbit hole. The final component of Tree of Thoughts is the search algorithm. Now that we have a tree of thoughts and a way to evaluate them, we use standard computer science search algorithms to navigate. Breadth First Search, or BFS, evaluates all current thoughts across a single level of the tree before moving deeper. This is excellent for problems where the depth of the tree is limited. Alternatively, Depth First Search, or DFS, explores a single path all the way to its conclusion. If the conclusion fails the evaluation, the system automatically backtracks to the last viable node and tries the next branch. This programmatic exploration is what makes Tree of Thoughts so incredibly resilient against logical hallucinations. When should you deploy Tree of Thoughts? Because it requires multiple model calls per step, it is computationally expensive. Therefore, it is best reserved for tasks requiring complex forward planning and multiple dependent steps. Examples include complex mathematical puzzles like the game of 24, where one wrong calculation ruins the outcome. It's also highly effective for software architecture and code generation, where multiple design patterns could be applied, and you need the model to rigorously evaluate the best one before writing the final production code. Tree of Thoughts is a masterpiece for fixing logical errors. But what about a different kind of hallucination? What about factual fabrication? LLMs are notorious for stating false information with absolute, unwavering confidence. Because standard generation outputs token sequentially, the model lacks a built-in mechanism to stop, look at what it just wrote, fact-check itself, and revise its claims before delivering the final output to the user. It just streams the data to the console. To fix this, we need a different framework. We need to build a self-interrogation pipeline. Enter Chain of Verification, or CoVe. If Tree of Thoughts is a chess player calculating moves, Chain of Verification is a rigorous investigative journalist fact-checking their own article before publishing. CoVe forces the model to systematically doubt, interrogate, and verify its own initial draft before finalizing the response. It acts as an automated editorial pipeline that intercepts the model's output, preventing fabricated facts from ever reaching the end user. Chain of verification operates in 4 distinct phases. Phase 1 is drafting the initial response. The LLM generates a baseline answer to the user's prompt using its standard generation capabilities. However, unlike a standard LLM interaction, this output is not shown to the user. This draft is quarantined. It is treated strictly as a hypothesis, a collection of potential facts that have not yet been proven. Phase 2 is where the magic begins, planning verification questions. The system analyzes the quarantined initial draft and extracts the core factual claims. It then generates specific, highly targeted questions designed to verify those exact claims. For example, if the initial draft claimed that the James Webb Space Telescope was launched in 2020, the verification planning phase will extract that claim and generate the question, in what year was the James Webb Space Telescope launched? Phase 3 is the execution of verifications. The system now answers the verification questions it just created. But here is the critical part, it must do this independently of the original draft. If it reads the draft while answering the questions, it will suffer from confirmation bias and simply repeat its own hallucination. By answering the targeted questions in an isolated context, often by querying an external RAG database, or simply relying on a fresh, highly focused prompt, the model retrieves the objective facts without being tainted by its previous mistakes. The fourth and final phase is the final verified response. The system is presented with the original prompt, the quarantined initial draft, and the pristine results of the verification questions. It is instructed to meticulously cross-reference the draft against the verified facts. It acts as an editor, striking out the hallucinations and rewriting the text to align with the truth. The fabricated launch date of 2020 is caught, corrected to 2021, and the final, factually secure response is finally rendered to the user. Chain of verification requires a moderate amount of compute, typically 3 to 4 distinct prompt phases, making it more efficient than Tree of Thoughts. It is the optimal framework for tasks where factual accuracy is paramount. This includes historical Q&A, pulling specific metrics from large financial documents, and critically, deploying AI in medical or legal domains. In these high-stakes environments, a hallucinated fact carries severe consequences, and the systematic, automated fact-checking provided by CoVe is absolutely mandatory. In conclusion, both tree of thoughts and chain of verification are essential tools in the modern AI engineering stack, but they patch entirely different vulnerabilities. Tree of thoughts is your algorithmic engine for fixing logical errors and poor decision-making through exploration and backtracking. Chain of verification is your editorial firewall for fixing factual inaccuracies and fabricated data through self-interrogation and revision. By understanding when to deploy each framework, we can build AI systems that are not only fluent, but relentlessly accurate. Thank you for accessing this system log. If you found this breakdown of AI reasoning frameworks valuable, please execute the subscribe command, like this video, and initialize notifications for more deep dives into advanced AI architecture. System shutting down.